everyone. This is the Physics 110 GR3D review. This GR is not posted on the online GR archive, unfortunately, but this is the GR that I took last year. So if you're reviewing for your physics GR next week, hopefully these videos will be helpful. In this video, I'm going to go over multiple choice questions 1 through 3. So let's get started. With number 1, we have a 5 kilogram water bucket. It's attached to an 88 centimeter radius, perfectly circular water wheel at rest. What magnitude of torque about the axis O of the wheel does the bucket exert on the wheel when the bucket is in the position shown? So obviously this question is talking about torque because it asks for the magnitude of torque. But what is torque? In case you don't know, torque is the force that causes an object to rotate. And so if we were to draw this picture a little differently, in other words, if we had the bucket up here at rest connected to this string, there's nothing, the force acting on that bucket is just the force of gravity, and the force of gravity is in line with our origin, and therefore it wouldn't cause it to rotate because it would just be going straight down. If it were taken, if the bucket were just a slightly over in this position right here, now you see that the string is going in this dotted line I just drew right here, but the actual force acting on it, the weight, is going this way. And so since the force of the weight is not in line with our string or directly going through our origin of our wheel, that means that it's going to have torque. And so if we look, I'm going to erase this now and only look at the bucket we're given. So now that we're given this bucket over to the right, it has a force of gravity going down like this. We have mg. So since this force is not acting directly in line with our origin, this is the line through the origin, and so any force that doesn't act in that line of the origin is going to create some torque on this bucket. So, or I guess it's exerting torque on the wheel. The bucket is creating the torque on the wheel. So we have our force down, and according to our equation that says torque is equal to, I believe on your equation sheet it says RF sine theta already. But if it didn't, I think that's how it is on your equation sheet, so I'm going to leave it at that. But that pretty much gives us all we need to solve this problem. So make sure you're looking at your equation sheet because it can give you a lot of hints on how to plug in some numbers and get some answers for these. But visually, what torque is giving us is the perpendicular, the R is the perpendicular distance from our force to our line through our origin. And so this is our R in this case that we want to take. That's the real R. When we apply it to this equation, RF sine theta, that's already factoring in the perpendicular nature. Because of this angle, it's using properties of sine, saying that sine of 55 is R over mg. But we can just plug our numbers into this RF sine theta and it'll do that math for us. So to find torque, luckily for this multiple choice problem, is pretty simple. It's just one plug and chug. So our R we're given is 88 centimeters. Our force is mg. And then sine of theta, you might be wondering which theta do I use. We use the theta over here because of how we're defining our R to be. If we used our 35, that would be saying that this distance here is our R. And that's not the R we're looking for. We're looking for the distance from our force acting on the object to the axis, which is this R right here. And so we need to use this 55 degrees instead of the 35 degrees. So we're going to do sine of 55. And then we're given the mass is 5 kilograms, so we can plug that in as well. 88 centimeters times 5. Gravity is 9.8. And sine of 55. If we do some math, we eventually get to the answer of 35 Newton meters. So if there were an answer choice to circle there, this is our answer to this question. Okay, moving on. Question 2. A dumbbell consists of two masses M connected by a rigid rod of negligible mass and length d. A student rotates the dumbbell around its center of mass with an angular speed omega, giving it an angular momentum L. The student then takes another dumbbell with masses 2m and length 2d and rotates it with the same angular speed omega. What is the angular momentum of the new dumbbell? Okay, so this question has a lot of words, a lot to take in. It kind of follows the same structure as questions you might have seen on previous GRs, where it's doing something to variables and making you do the algebra to figure out how changing one of the variables will change the value of the equation itself. So if we look at what concepts we're dealing with in this question, we're given angular speeds, we're given angular momentum L, we're given masses and distances, and again, angular speeds, and we're trying to find angular momentum. And so everything's in terms of angular, go figure, this is the angular unit. But a really good way to look at this problem is to draw it out, because it's hard to synthesize the words sometimes when you can't see a picture. So what I'm going to do is I'm going to draw this dumbbell with two masses M. So that's what a dumbbell looks like, connected by a rigid rod of negligible mass and length d. So we know the length of our entire dumbbell is d. Okay, so a student rotates the dumbbell about its center of mass. So if we're saying the center is right here, we're rotating it with some angular speed omega. And when we rotate something, it gives us angular momentum. Now, you can again look at your equation sheet for this. Angular momentum L is defined as I omega. So that doesn't give us much, though, because we don't know what I is. But we also know that these, we just have 2 point masses M. So when we're dealing with point masses, it's, let's see, looking at our equation sheet, we have I is equal to mr squared. That's going to be the case for most of these, unless they specifically say that it's like a disk or something like that that has a different I value. But since these are point masses, we're going to just use mr squared. So for angular momentum, we're just going to substitute that in, mr squared omega. Now the thing is here, we got to figure out what that r is, because none of the variables they gave us relate to r, but they did give us a length d. And so if the length d is pertaining to the entire dumbbell, to figure out the angular momentum of just one of these masses, let's take this left one for example, the r is the distance from the mass that you're looking at to the center of mass. And so be careful not to just plug in d for this, because d is the length of the whole dumbbell. This is also why it's good to draw a picture, because then we can see, if we're looking at the left mass, the distance from the mass to the center of mass is just that, which is half of d, because we're only looking at one side of it. So we can plug that in. We can say m, I'm going to call this d over 2, because we're splitting it in half, and that whole quantity is squared, because it's r squared omega. Okay? So I'm going to leave it like that for now. I'll simplify later when we plug in some other things. But now we want to look at the second part of our problem. We're taking another dumbbell. This time we're doubling the masses on both sides, and we're also doubling the length. So if we wanted to draw another picture, I have 2m connected by a rod. This obviously isn't proportional because I did not draw it twice as long. Oh, yeah, length 2d. Okay, and it rotates it with the same angular speed omega. So that means whenever we write our new angular momentum equation, here, let's call this the first case of angular momentum. And now that we calculate our new angular momentum, we can leave omega as the same thing, because it stayed the same in both of our problems. So if we look at the angular momentum for this one, we'll call this angular momentum 2, it's still mr squared omega, but now our mass is 2m, and our r, if we take our center of mass here, the distance from one of those masses to the center of mass is now half of 2d. So it's just d squared omega. So now, let's look here. To figure out the total angular momentum we just figured out the angular momentum for one of the masses. So it's pretty simple with this one. All we have to do is double it because the masses are the same on both sides, so it would give us the same equation. And so the total angular momentum for 2 is just 2md squared omega plus 2md squared omega, or, in other words, 4m d squared omega. So now I'm going to go back up here to my angular momentum 1 and simplify this because we need to figure out the relationship between L2 and L1. So, if we simplify this, we get L1. Well, first of all, we got to double it because, again, md over 2 squared omega is just one of those masses. So, if I were to double it, it would give me 2m d over 2 squared omega. And so now if we simplify that, we get L1 equals 2m. Distribute that exponent. So I'm going to get a d squared over 4 omega. So if I divide 2 by 4, we're left with 1/2 md squared omega. So now we have L1 and L2 simplified, and now we can see the relationship between the two of these. So there's two ways of doing this. One way is you can just do L2 over L1 to figure out the ratio between the two. Another way, if you can see it, is md squared omega is the same in both of these. The only thing that differs is the 4 and the 1/2. So if you can just look at L2 and be like, oh, this is 4 md squared omega and L1 is 1/2, what would I have to multiply L1 by what would I have to multiply 1/2 by rather to get 4? And so the answer would be 8L. Again, you can find this by just doing L2 over L1 or 4 divided by 1/2, which would also give you 8. And that's the answer for this question. Now, number 3, a solid sphere of mass m starts at rest and rolls without slipping down a hill of height h. What is its speed at the bottom? Okay, so whenever we're looking at questions like this, I have a mass that's starting at rest and rolling, and then we're figuring out a final speed. So when you're seeing all these words come together, starting at rest, finding speed, and it's giving you a starting h, it should be triggering a sign that you should be using conservation of energy in this question. Because we're starting with a certain amount of energy when it's at rest, and then it's getting to the bottom of a hill, and that energy will be conserved, all because of this phrase right here, rolls without slipping. That means that there's no friction, and so it's not losing any energy when it's going down this hill, so all the energy is going to be conserved. So if we're looking at our conservation of energy, we have our basic equation of U plus K, these are initials, equals U final plus K final. In other words, potential energy initially plus our kinetic energy initially is going to equal whatever potential and kinetic energy we have at the end. And so we can kind of just start plugging in numbers here of what we have. So when we are imagining this ball at the top of a hill, it's at rest, starting at height h. So when it's sitting up there at rest, there is no kinetic energy. So we can take that out of our initial, because it's starting at rest. However, we are starting at a certain height h, which means we have some initial potential energy. So potential energy is mgh. Now, looking at our final, when the ball gets to the bottom of the hill down here, it's now at ground zero, so we don't have any more potential energy. It's not raised above the ground by any height h. But we do have kinetic energy at the bottom. Now, careful here, there's two types of kinetic energy. Now that we're in the rotational unit, there's there's kinetic energy, and then there's kinetic rotational energy. And so we have both of them here because we know this ball is rolling. So we have a 1/2 mv squared, which is what we did last unit. But now we also have a 1/2 I omega squared. Again, you can get that from your equation sheet. That's just rotational kinetic energy. So now, this is just a lot of manipulating variables because we need to get to v. We need to figure out what v equals because we want to find the speed at the bottom of the hill. So, let's see here. I want to get rid of that I because if we look at our answer choices, everything's in terms of g and h. And so the only thing that messes that up is the I and the omega. So we need to get rid of those by replacing them with something. So I'm going to copy this. Now, my I, this is saying it's a solid sphere. So if we look at our equation sheet, we find our I for a solid sphere to be 2/5 mr squared. Okay. And now we need to figure out what that omega is, because again, our answer choices are only in terms of g and h. And now you might wonder, oh, we just introduced an r squared into this, but our answer choices don't have an r. Good thing about that is when we do omega, we also know omega is v over r. Again, that's on your equation sheet. And that whole quantity is going to be squared. So now you see when we distribute that squared to the v and to the r, we're going to be able to cancel those out. I'll write it out so we can see it. So if I have 1/2 times 2/5, I'm going to cancel these 2's, and I'm just going to make this a 1/5 mr squared. And then to distribute that exponent, it's going to give me a v squared over r squared. And so now, r squared on the bottom, r squared on the top, those cancel. So now we're left with mgh equals 1/2 mv squared plus 1/5 mv squared. Okay, so now we need to get to v. It's a lot of simplification. We're going to get mgh equals, let's see, 5 plus 2, so 7/10 mv squared. If I look at this now, I see I have an m on both sides of my equation. So if we divide by m on both sides, we can get rid of that. So now I'm just left with gh equals 7/10 v squared. Need to solve for v, so I'm going to multiply by 10 over 7 on both sides. So v squared is equal to 10 over 7 gh. And if I take the square root of both sides, 10 over 7 gh. And if we look, boom, we got answer C right there.